Okay, good afternoon everybody, and welcome to the last lecture on audio coding this semester. So, last time we finished psychoacoustics, and now we want to continue with prediction and lossless audio coding. Okay, so, this is another principle of audio coding which we want to talk about today. So, prediction is another way of using redundancy in the signal, meaning statistical dependencies between samples. Right? So when we have memory between samples, then we get correlation. And when we have more memory, we say we have more correlation between samples. So when we look at the power spectral density, which is basically the spectrum, the power spectrum of our signal, and we see that it has a flat spectrum like white noise, then we know it has low redundancy, right? Because white noise basically means independent samples, no memory. So we can compute the autocorrelation function as indicator for this memory of our signal. So that's defined by this autocorrelation integral here. So this integral is used for continuous time signals. But if we look at discrete time signals as we usually have, then actually the integral turns into a sum. And both have in common that we take the signal and its shifted version, multiply it time point wise, and then integrate or sum up, basically taking the average. Right? And if you imagine you have white noise and you just square it, don't shift it, then you get the noise power in this way. But if you have noise and you shift it a little bit, then this leads to the fact that you have equally positive and negative values, and they basically over time cancel each other out, and then you will have zero average. Right? Make sense? So if you purely have purely random samples, and you don't shift them, then you have a square. So it's all positive. So you have a positive average over time. If you shift it a little bit, then there's no squaring anymore. And you have positive and negative values, they cancel out over time. So that means if you have noise, then this autocorrelation function will be peak at time lag 0. Right? And everything else will be 0. So this basically in continuous time will be a Dirac pulse, and in discrete time will be a unit pulse. Yeah, so when you go from the time domain to the frequency domain, you just apply the Fourier transform to this autocorrelation function. Then instead of having this multiplication, you get the power spectral density. Basically, the multiplication in time domain becomes or rather here, you have a convolution in the time domain, a convolution with a flipped version of the signal. So here, basically it almost looks like a convolution except for the sign here. So this corresponds to a convolution with a flipped version of the signal. So this turns into a multiplication in the frequency domain, and this flipping is equivalent to conjugate complex in the frequency domain. So basically you have the spectrum times the conjugate complex version of the spectrum, and when you have a complex number and you multiply it with this conjugate complex version, what do you get? C times conjugate complex of C. You remember? Yeah, it's a magnitude squared. Exactly. So basically, then you have spectrum times spectrum conjugate complex, and that's the magnitude squared of the spectrum. So this is the power spectral density. Make sense? So here this is just having this name, power spectral density, because it's the power in the spectral domain. Yeah, so this is what I just said. Correlation is convolution with the signal at its reverse version, in its time reverse version. And in the DFT domain, this means multiplication with this conjugate complex version. Right? And that's why we get the magnitude squared. So here you can see it graphically. Here on the left-hand side you see two signals. On top you have high redundancies, which means a lot of memory. And you can recognize the memory with a similarity between neighboring samples. It has only slow change. Here it's a sinusoid. Here on the bottom, this should be white noise. Basically, you have totally random samples. And when you look at the autocorrelation function, when you have the sinusoidal function, again becomes a sinusoidal function as autocorrelation function. If you take this random noise, this will become this Dirac pulse, right, as I just mentioned. So this is the autocorrelation function, and if you then take this autocorrelation function and apply the Fourier transform to it, then this Dirac pulse in the frequency domain becomes flat, constant over all frequencies, as you would expect for a noise signal, right? It's flat. And for the sinusoidal signal, we get two peaks in frequency. Those peaks correspond to this frequency of the sinusoid. Here, one's at the positive frequencies and one's at the negative frequencies. Right? Makes sense? So here in the frequency domain, we actually have an indication about the redundancy. When you have a flat spectrum, that means you have no redundancy. If you have a very peaky spectrum, then you have a lot of redundancy. Right? So that means flat spectrum is bad for compression, peaky spectrum is good for compression. Yeah, and the memory, so far we used in subband coding, right? This peaky spectrum can be used in subband coding because those peaks only appear in a few subbands, and the rest basically has no signal, right? So we can focus on those few subbands where we actually have a signal. We can also use instead a predictor. If you have memory, not only is the spectrum peaky, but also that means the coming sample is predictable, right? You can use this memory to predict the next sample, and instead of transmitting the sample, you only transmit the prediction error, which should be ideally 0 or very small. Right? So this is what you can see here. You have some input signal X, and here you have some predictor which tries to predict this current sample based on past samples which also the decoder already has decoded. Right? So here we have an estimate for the coming sample, and then we just transmit the difference between the estimate and the real sample. So this is E, the prediction error. So then we encode the prediction error instead of the actual sample, transmit it with fewer bits, because ideally it should be very small. Then in the decoder we decode this error, and then we have the same predictor. So ideally it has the same reconstructed past samples as the predictor in the encoder. And then it also should predict the same predicted value. Makes sense. So those two should be identical. So then what the encoder subtracted, we can simply add again, and then you get the original sample back. Make sense? So if we have a sinusoid, for instance, then this predictor will have, in the beginning of the sinusoid, when we turn it on, it needs a few samples to figure out the prediction coefficients. So then we will have an error. But after it figured out that this is a sinusoid, then basically the coming samples should be perfectly predicted. And that means we have a prediction error of 0. So we just have a sequence of zeros which we can transmit with, in principle, 0 bits. Right? And then in the decoder, we just need to reconstruct the beginning where we have an error. And then this predictor also figures out that this is a sinusoid and just continues to produce sinusoidal samples. Right? Basically in itself. So this can predict the sinusoid function because it knows how it looks like without the help of the encoder. So basically this continues with 0 bits until the sinusoid ends, and then again you get a prediction error which you need to transmit to basically tell the predictor to stop. Make sense? So this predictor is basically a model of the signal. This predictor should be able to reproduce the original signal with the help of a small prediction error. So this works fine if this is actually a good model of your signal, because this is supposed to produce the signal that you wanted to listen to. So this is actually a surprisingly simple model, and it's a question if this is actually working. We saw it actually works quite fine for a sinusoid, because the sinusoid is perfectly predictable. But then you also find that many audio signals can be represented by a limited number of sinusoids. Right? So we have more than one sinusoid, but if each sinusoid is perfectly predictable, then also the sum is perfectly predictable. You just have to have a predictor which is capable of predicting more than one sinusoid. Right? Yeah, and then of course we need to figure out how to build this predictor. Like what's behind it. Have you seen such predictors before? Speech or audio predictors? First time? Okay. So let's take a look how to build a predictor. So in the encoder we have our predictor and the prediction error. So here E is the prediction error. It's computed as x minus x hat, x hat the predicted value, and the predicted value is simply the output of an FIR filter. And here we can see it's the sum of coefficients times past samples. So this is basically an FIR filter. But it's only based on past samples because we start the J at 1 and not 0. Right? When we have usual FIR filters, they start at the current sample. This one starts at sample number 1, which means one sample in the past. Because we wanted to have as basis only past samples, which also the decoder has from past decoded samples. Right? Otherwise, prediction would be trivial. We would just take the value itself and subtract it from itself. So here we try to estimate the current sample based on past samples, using this weighted average or weighted sum of past samples. Make sense? So here we simply have an FIR filter, basically like in our filter bank. Remember, for our filter bank, for each subband we had a filter, but it was fixed. Right? Here, instead of a bank of filters, we just have one filter, but this filter is adaptive, as we will see. Because here the H depends on the signal to predict. So this is the decoder. The decoder has the same formula for our predictor here, same weighted sum of past samples, and instead of subtraction we have an addition here. And the goal here now is to minimize the mean squared error, here E squared and the expectation of it. So this is the mean squared error, by optimizing the filter coefficients H. So we want to find the coefficients H which minimizes this mean squared error power. And again we take the error power because this leads to a simple closed form solution. Right? It's not like mean squared error would be the best error function here, but it just leads to a simple closed form solution. Yeah, and the solution can be seen here. So we take our error power and take the derivative, and it's minimum when the derivative is 0. Right? So if the error power goes down and at some point it's minimum, then we have 0 derivative. Make sense? When you have a minimum, the derivative needs to be 0. So this is how we recognize a minimum. It can also be a maximum, but we are not interested in maximum, just a minimum. So we know that the mean squared error is just x minus x hat and the expectation of it. Right. And x hat, again, is this weighted sum. So here we have x minus x hat. And what we do in the next line is we reformulate the square. So if we take the derivative of this function here, we have the outer derivative times the inner derivative, so the chain rule. Right? So the outer derivative of this expression is 2 times x minus x hat, is this part, and the inner derivative is dx hat to dhj. Right? And because x hat to dhj, remember here we have here's our sum. So here are our sums. Remember that we have x is only dependent on the j's per sample for coefficients hj. Right? So x hat derived with respect to x of n minus j means we just keep this coefficient. Right? So when you take a look at the sum here, x hat derived derivative with respect to x of n minus j, there's only one part in the sum, and that's with the sum hj. Make sense? So that's the inner derivative, this hj. So that's why we have this x of n minus xj, x of n minus j. And we want to have this to be 0, so we just plug it in here. So 0 is expectation of x minus x hat times x of n minus j for all j between 1 and capital N. Right? This is our requirement. Yeah, and now we can actually use our definition of our autocorrelation function Rxx of k. It's simply the expectation of x of n times x of n plus k. And we see here we have something equivalent. Right? We have x of n times x of n minus j. Right. So this times this then gives us this expression here, where I just replace k by k. And then x hat times x of n minus j is then the sum. Remember, x hat was simply the sum over hj times x of n minus j. So here, that's why we get this sum over the autocorrelations between this index j and this index k, which we have for our autocorrelation function. So this is then valid for all k between 1 and n. Make sense? So then we can just bring this sum on the other side, or vice versa. Then we have Rxx of k equals the sum of hj of Rxx of k minus j. Make sense? So this is now actually our solution. This formulation now leads us to the hj. So it's really simple, right? All we need is autocorrelation functions. So maybe you can add this here. Yeah. And here we have k equals 1, comma. Let's actually start with 0. So now we can put it in terms of a matrix equation. We just take all the correlations into a matrix, which we call RxX, which contains all the autocorrelation shifts from 0 to n minus 1. And then we can rewrite it in this form. So on the left-hand side, we have the correlations from 1 to n. On the right-hand side, we have the correlations from 0 to n minus 1 times our optimum h. Okay, so actually that means we still have the n here on the right-hand side. Make it correct. Okay, so that means now we have a simplified version using our matrix formulation. Rxx equals our autocorrelation matrix times the vector of optimum coefficients. Right. And that means we obtain our optimum coefficients by just inverting this autocorrelation matrix and bring it on the other side, which is what we see here. So we have Rxx from the left-hand side, we multiply it with Rxx inverse, and that gives us our optimum coefficients. Right. And you can read more about it, for instance, in this book from Monson-Hayes, Statistical Digital Signal Processing and Modeling by Wiley and Sons. So this is actually a famous formula to obtain the coefficients for our filter. Yeah, so this also leads to the orthogonality principle of prediction. It means the prediction error is uncorrelated to the signal, otherwise the prediction could be better. And you can read, for instance, in this Wikipedia link about this principle. That means the prediction error and the n-pass signal samples are uncorrelated if we have the optimal prediction coefficients. So here you can see this is the expectation of our error multiplied with past coefficients. And that means the predicted signal is a linear combination of the past input samples. So here we know this, x hat is a linear combination of those samples, and that means that the expectation of the error and the prediction itself is 0. Right? So the prediction, error, and the predicted signal are statistically orthogonal to each other. So this is how we can recognize the optimum predictor. If this is not the case, if this would be non-zero, then the predictor would not be optimal. Right? So this is a requirement or test of optimality. Yeah, and you can also derive this so-called Wiener-Hopf equation, which we just saw, using pseudo-inverses. Right. So we can just put our signal into a matrix, into a tall matrix. So B basically is the length of our signal, maybe a block for the sake of the computation. So this block might be 7,000 samples long, or maybe a few hundred, depends. And the width of this matrix depends on the number of prediction coefficients. So for instance, if we have 10 coefficients in our predictor, then this matrix would be 10 columns wide. So 10 wide and maybe a few thousand high. So this would be a tall matrix. And then on the other side, we have a desired matrix, which contains the sample that we want to predict. So this is the future samples for each row. So you can see in the first row we have all samples up to x of n minus 1. And the one to predict is x of capital N. Right? So this is for each row, this is the next sample to be predicted. So if you now take this matrix here and multiply it with our prediction coefficients, then it should predict our next sample as close as possible. Right? So this is our formulation. We take this matrix A, multiply it with our column vector of prediction coefficients, and then we should approximate this vector D. So we can never get exactly D because this is overdetermined. We because we have a tall matrix, but we can approximate it. Right? Yeah, basically we reformulated convolution in this way with a matrix multiplication. So this matrix multiplication here is now representing our convolution. Right? So it's reformulated as a convolution because in the next step we can use pseudo-inverse from matrices. Right. So here you have more equations than unknowns, and this is the sequence of next values which you want to approximate. Yeah, and we can again obtain a closed form solution of this equation using Moore-Penrose pseudo-inverse. So in matrix multiplications or matrix equations, we have this as a closed form solution for a mean squared error solution. So when we look at this result, basically we take the equation that we just saw and multiply both sides with X transpose. So remember, X was a tall matrix, then X transpose is a fat matrix, and when we multiply a fat matrix by a tall matrix, what size matrix do we get? Well, it corresponds to a square matrix with a short side. Right? So if the tall matrix is 10 wide, then the transpose will be 10 high, and that means A transpose X transpose times X will be 10 by 10. Make sense? So we have fat matrix times tall matrix gives us, in this example, a 10 by 10 matrix, X transpose X. So we have a square matrix which is now small, corresponding to the size of H, which is, for instance, also 10 coefficients as a common vector. And then we can invert this. So we assume that this 10 by 10 matrix is invertible, which usually it will be. And then we can just bring it on the other side, and we get a result for H. Right. So we have a solution which actually, again, corresponds to the solution for the mean squared error approximation. Simple, huh? So basically the Wiener-Hopf solution for limited length signals. So this actually has the advantage that we get a precise solution for limited length signals, unlike the first approach where we have the correlation matrix. For the correlation matrix, in principle, we need infinitely long signals. Yeah, and when we look at this X transpose X, it indeed converges to the autocorrelation matrix that we saw if we have infinitely long signals. So if the length of our signal goes to infinity, then this X transpose X indeed becomes the autocorrelation matrix. And the X transpose D, which we have on the other side, converges to the cross-correlation matrix or autocorrelation matrix 1 in the future. Right. So this results in the Wiener-Hopf equation that we saw before. If B, the block size goes to infinity. So the signal length, if the signal length goes to infinity, then both solutions are the same. But they're not necessarily the same for finite length signals. Yeah, so this is what I just said. We have a quadratic matrix, which we can hopefully invert, and then H approximates D in a quadratic error sense. So again, an easy closed form solution. So now we have our coefficients which allow us to predict the next sample. By the way, you could use the same approach, for instance, to predict stock market prices. And this is actually what many banks do. They try to predict stock market prices using this type of prediction. Actually, they use usually much more sophisticated prediction, but it's the same principle. Right? So you could use this kind of prediction to become rich. if it does the right prediction. And that's always the question, right? Is the model fitting to the signal that you want to predict? So this does prediction, but it's not guaranteed that it does a good prediction. Yeah, so the quality of the prediction is measured by the coding gain. Right? Coding gain basically is a measure of how much we gain by applying prediction compared with no prediction. So imagine you have a signal with no prediction, then you have the samples itself, and you spend a certain amount of bits to encode those samples. And you can do the same for the prediction error. And you hopefully spend fewer bits on the prediction error. Right? And the number of bits per sample that you save is basically the coding gain. Right? So this is actually a measure of the quality of the prediction. Yeah, you can also now estimate the coding gain by looking at the prediction error power. Again, as before, sigma e squared is the expectation of x minus x hat squared. And we can rewrite it as expectation of x squared plus x hat squared minus 2x times x hat. Right? The same thing. So you can just multiply out this squared. And then you can use this decoder reconstruction error, x equals x hat plus e, and we get expectation of x hat squared is expectation of x hat times x of n minus e of n, right? So this is also x hat. And next we can then replace or use the orthogonality principle by saying expectation of x hat times e is 0, and then we can replace x hat times e. So we have this term here, basically disappears here. So we factor out those here, get this equation, and then we see this last part here disappears because of the orthogonality principle. Right. So we get then e of x hat squared equals e of x hat times e of x times x. So we get this equation here, and then we can plug it into our equation for our prediction error power from above. So we take this equation here again, so this is the same, and then we can draw in this expectation here. So we have e of x squared plus e of x hat squared minus e of 2x x hat. And here we now can see that this e of x hat squared is already here, so we can replace it by this expression. And we see now we have minus 2x hat, x hat, and here we have plus e x hat x. So one of them cancels, so what's left is e of x squared minus e of x hat. So this is now our estimation for our prediction error power. Right. So this is what we get. And we see that the first term is the signal power. So e of x squared is the signal power. And the second term is this e of x hat. And x hat again can be written in terms of our prediction sum. Right? Here we have the h, our prediction coefficients. And we see that now x times x of n minus j is again our autocorrelation function. So we can replace this e of xn times x of n minus j by rx of j. Right? So what's left of this expectation is simply the sum of the weighted correlations, autocorrelations. Or in vector form, we have our coefficients transposed, which means it's a row matrix, a row vector, times rxx, and column vector. Right? And we know that this h opt, we already calculated using the Wiener-Hopf equation here. So we can replace this h opt by this expression here. first we need to transpose it, and then we have RxX transpose times RxX transpose inverse. So we have it here. Just plug it in. And that means the total equation here is the first term, sigma x squared, minus this term here, RxX transpose, times the matrix, the autocorrelation matrix, inverse transpose, times RxX. And because the autocorrelation matrix usually is symmetric, this transpose usually doesn't matter. Yeah, so this is now our error power, which we now estimated. And now we can use it to compute our coding gain from it. So here we have the prediction error. And actually we get an interesting result from this book of J and Moll for the limit of this prediction error power for a prediction length of n going to infinity. So for an infinitely long predictor, which means the predictor is as good as possible. And this is the result here. So this result looks at the power spectrum, SXX of e to the j omega. And it goes over all frequencies from minus pi to pi. And it has this exponential function in front of it. And so here we get a formulation for the signal error power in the frequency domain. So here it also depends on, again, how flat our spectrum is. So now we can apply the log function to get rid of the exponent here, and we see the log of the error power, prediction error power, is simply the integral over all frequencies of the log of the power spectrum. Right. And when you look at this equation here, this log of the power spectrum, this is comparable for the number of bits we need in subband coding. So for each subband, we have a power which we need to encode using our entropy coder, for instance. And the number of bits that we need for our entropy coder is proportional to the logarithm of the size, or the power. Right? So for instance, if we have a power of 4, then we need 2 bits, right? From 0 to 4 to, well, actually 3 bits. 2 bits. Goes up to 4. If we have 16, 0 to 16, we need 4 bits. So 0 to 50. So you can see that's proportional to the log of the power in each subband. Yeah, so here with prediction, we get a coding gain, or a number of bits for the prediction error, which is comparable to the bits for subband coding. And that means the coding gain depends on the spectral flatness measurement. So again, we have a description of the number of bits we need for the prediction error, which depends on the spectral description. And basically this shows that in the end, it doesn't matter if you do subband coding or prediction. It only depends on the signal. What spectrum we have from the signal. How many bits we need. Okay, so this is the number of bits we need in the limit for an infinitely long predictor or with infinitely fine subbands. And in each case, we need about the same number of bits. So this is an interesting result. Yeah, so this is the number of bits for predictive coding here. Right. So here you can see it, this log of sigma e squared. You could also say that this corresponds to the average word length for each sample in the time domain for the prediction error. Right. And this can be viewed as the number of bits for subband coding because it looks at the spectral domain. And since we have this equality sign here, that shows us that the amount of redundancy is given by the signal and not by the method. Right? So the redundancy is method independent. It's a property of the signal.
quiz we had one example relating to the spectral flatness measure, and it says calculated. We found the formula from Wikipedia and the result didn't give the same answer. Is it possible to solve them?
Which did you try to compute?
I mean, we tried to calculate spectral flatness measure using power spectral density of FFT.
Yeah.
I have the question if you want, I can show.
Yeah, maybe later.
Ah, sure.
Yeah. So, yeah, basically this spectral flatness determines how much gain we can obtain. Right. Yeah. So using predictive coding or subband coding, we can take advantage of the redundancy in our input signal. Basically, prediction reduces the redundancy in our signal, and the same in subband coding because we do the downsampling in each subband. Right? So that limits the amount of information that we have between neighboring samples. So redundancy and the input signal is independent of the method. And predictive coding and subband coding will achieve the same results for n, capital N, towards infinity. So this is the number of subbands or the order of the prediction. But we will have different properties from finite n. So for instance, if we have a signal with only few sinusoids, we will get better prediction with finite n. Because predictors are really good for sinusoids, for a limited number of sinusoids. But if you have narrowband noise, basically narrowband noise, we have very dense sinusoid, basically infinitely dense sinusoids, and then prediction is not so good. But subband coding will be better, because subband coder can easily cover this narrowband noise with a limited number of subbands. So it depends. Yeah, so prediction or predictive coding can now easily be applied to lossless coding, unlike subband coding. Right? So the definition is the decoded and the original signal are bit identical or integer identical. So the decoded actually has the same exact numbers as the original. So for instance, if the original audio signal has integer values, then lossless coding only removes redundancy and no psychoacoustics or irrelevancy removal is done, right? Or in any case. Right? If you have lossless coding, this is basically a mathematical process which is limited to the redundancy reduction. And prediction is convenient for lossless compression because you can easily obtain an integer to integer prediction. So if we have an integer sequence coming in, we can easily get integer valued prediction error. And the prediction error can easily be made integer values, as we'll see in a moment, and the inverse prediction results in the original integers. So here you can see it. So here we have our predictor. You can see here it's based on past samples because the first sample goes already through the delay element. And you can see the prediction output here now isn't going directly to form the prediction error, but only after a rounding element. Right? So we have an x, which is an integer value. Here we have the predicted value, which is float. And to avoid having the error being float, we just apply a rounding operation, and then the prediction error will also be an integer value. And then this e, this integer valued e, will be encoded, entropy encoded, and then stored or transmitted. Right, you can see it. So in this way, we obtain everything integer valued. So in that sense, it's not a quantization, it's just rounding to an integer value. We have a predicted value, which is float, and then we make it integer valued by rounding. And the decoder has the corresponding structure. Remember, we need to have the same exact predictor in the decoder, and that means we also need to have the exact same rounding function in the decoder to be able to add the exact same value that we subtracted in the encoder. Right? And since we have the same rounding, the reconstructed value x is identical to the original. Right? So we avoid any quantization. We just have this rounding in this sign path, and since we have the same rounding, we get this exact same value back using finite number of bits for the entropy coding. So this is how we can easily make a lossless coder. But the exact same algebra is important. So that's why, for instance, the rounding and the computations here need to be standardized. We need to really take the exact same operations, otherwise we might have some errors. So for instance, we could use some IEEE standard algebra and rounding for both sides, so that the implementation is really exactly the same. Yeah, and then there are different approaches to predictive coding. So how do we adapt the HJ for the real-world signals, or predictor? Right. So we can apply the Wiener-Hopf equation for a block of a certain length. Right. Subdivide our signal into blocks of a certain length and compute those HJ for each of those blocks, and then transmit those coefficients as a sign information. Right. For instance, most freeware lossless audio coders use this approach. And if we have a long block size, this is good for a low site information rate. And a short block size is good for a good signal adaptation. Right? So there needs to be a compromise, a good compromise for the block size. So this approach is called linear predictive coding, or short LPC. And for speech coding, it usually has blocks of length of 20 milliseconds. So it was found that for speech, 20 milliseconds is a good size. And this approach is taken for the speech coding part, for instance, for the MPEG Universal Speech and Audio Coding, or USAC coder. Its audio coding part actually uses tools from AAC, which we already saw. So this is basically then for the speech coding part. And it's also used in the 3GPP enhanced voice services, the EVS standard. Also on the speech coding part and in the adaptive multirate coding, AMR, which is an ITU standard. Yeah, and here I have a Python example that shows you the original, the prediction error, and the reconstructed for 20 millisecond blocks and LPC. So you can actually listen to how the prediction error sounds like. So I will show you. So first, edit, LPC. So here's the Python code. And you can see here I'm setting the predictor length to 10. So we have 10 coefficients for our predictor. Here, in line number 6, we read in this file, the example file. Here I have speech. X is the signal, Fs is the sampling rate. Then in line number 8, I normalize it to float numbers between -1 and 1. And the first thing I do here is play back using our sound library. So here you can actually hear the original. So then I'm setting up the memories. Here E for the prediction error. Blocks is the total number of blocks in our signal. So I'm taking the length of the signal and divide by 640, because 640 corresponds to 20 milliseconds. Here I'm using state as the memory state for our predictor. Remember, the predictor looks at past samples. And we want to be sure to have the predictor be at the beginning of a new block, being able to look at samples from the previous block. And that's why we need to store past samples at the end of one block for the beginning of the next block. Right? So this is the, what's done with state. And here are our prediction coefficients. So here we have 10 coefficients for each block. Right? So this is a matrix which contains the 10 coefficients for each block. So we have many, many coefficients in this way. So here now we have our for loop over our blocks of our signal. So first you can see I'm setting up this matrix A. So this is basically the capital X that we saw in the slides. And this A gets assigned the blocks of samples here. You can see here n is the nth row, and the nth row gets a piece of the signal, this block of the signal here. Starting at sample number m times 640, m is the block number, and then the next coefficients. Okay, so 10 coefficients. So we have this matrix, each row contains 10 coefficients, and it has roughly 640 rows according to our block length. Yeah, and here this is the desired matrix which I'm setting up then. This contains the next samples for each row, this D. And here I'm computing now the prediction coefficients for the nth block. So here you can see I'm having A transpose times A, matrix product, taking the inverse and multiplying it with A transpose times D. Right? So this is exactly the formula, the Wiener formula that we saw. Then I'm computing here the coefficients for a prediction error filter. Here you can see this is an FRR filter. I'm taking the current sample and subtracting the predicted value here, minus H. This is the predicted value. So that's why I call it HPR. So this is the prediction error. Yeah, and then here in this L filter, I'm actually conducting the prediction. So I'm taking this prediction error filter, applied in the feed-forward path here. The feedback path is 1, so it's not used. Here is the current block, which is filtered, and the output here is then going into my prediction error array. Right? So we have 640 samples at the right point. And this L filter gets the current state as input and then also returns the state at the output to be read in at the next block. Right, so that the filtering across block boundary is going seamless. Make sense? So this is actually an important trick for blockwise processing, that you actually keep the state across block boundaries. And the actual formula for computing our prediction coefficients is here in line 28. Right? So here you can see this is A transpose times A inverse times A times D. Make sense so far? Yeah, basically after this for loop finishes, we are done. Right? Then basically we have our signal E. Now we can compute the average squared error by just taking E transpose times E and divide it by the number of samples. Then we have the average squared error. We compare it with the mean squared signal power, which I do in the next line, to estimate our coding gain. And then this coding gain is basically the signal to error ratio. And simply divide the two. And then I'm playing back the prediction error as sound. So you will hear a clear difference to the original. Then I plot it. And the decoder here is really simple because I don't need to compute the H anymore. Remember, the H is transmitted as site information to the decoder. And that's done here in this example by simply taking this matrix H. Right? I have this here, this matrix H, where I stored all the coefficients for all the blocks. So here I'm again forming this prediction error filter for each block. I'm just reading it out from this matrix. And then I'm doing again this L filter. The filtering is doing the prediction. But now instead of having my filter in the FIR part, I have my filter in the IR part, in the feedback part. Remember, in the decoder, I have the predictor in the feedback loop. Right? And that means I have it in the feedback in the IR part. So that's why I have it here. Right. Here as input, I have my error. Again, the same trick with the state. Yeah, and this also shows you why this is exactly the inverse. Because here, this is the numerator of our transfer function, and this is the denominator. This is the denominator of the transfer function, and this is the numerator of the transfer function. Alright? Or denominator, numerator. So, in the encoder, each PR was here in the numerator, and in the decoder, it's in the denominator. So it cancels. Right? If you have transfer function from encoder times transfer function in the decoder, numerator and denominator will cancel. And all what's left is 1. So it shows us that we should get the original back. Questions for this code? It's easy, right? So basically, we have line 62 for the decoder, and you have line number 28 for the encoder coefficients. And the actual prediction error is computed in number 30. So just those lines here. And yeah, here the coefficients are computed in 60, and the decoder is actually happening in line number 62. So now we can actually execute it and listen to it. So let's try Python 3.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So that's the original. Prediction error. So here you can now see the plot of the two. You can see in blue the original, and in red is the prediction error. And you can see the prediction error is indeed much, much smaller. Right? And that shows that the prediction worked. Because these much smaller values can be encoded with much fewer bits. Right? So we get a coding gain. And you can also hear it. You can also hear it.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
So this is the decoded. So the decoded indeed is identical to the original. Right? So the decoder was actually able to reconstruct this original just from the encoded prediction error. Right? It's kind of amazing, right, that it was able to decode the original from this noisy and much softer prediction error. You could also hear that the prediction error sounded more noise-like. And that's because noise is very difficult to predict. All the tonal parts of speech are easy to predict. So they're very small. But the noisy parts are not so easy to predict. And that's why you have a larger error there. And that means it's dominated by noise. Okay. So, back to the slides. Here are some references. So, here you can see a link to 3GPP, a Wikipedia link, which has a nice description about it. There's also further links. Then MPEG USAC. We also have this Wikipedia link and ITO AMR. So you can take a look. Yeah, and then we come to LMS approaches to predictive coding, but now not using blocks, but using backward adaptation. It's called backward adaptation because it only looks at past samples for adaptation. So the LMS, or least mean squares method, is an online update which is derived from the stochastic gradient descent method, which minimizes the prediction error. So it has this normalized LMS update formula. And here you can see the new coefficients for the next time step are the old coefficients, but updated by this formula. And you can see here, in this update formula, you can see x minus x hat. So this is the prediction error. Right? It means the larger the prediction error, the more update we will get. And you see here x of n minus j. So it also depends on the size of this corresponding sample. So here hj is updated, and the update size only depends on that corresponding sample. Right? So it's actually quite a simple formula, but it's applied for each sample. Right? So this is now not blockwise, but for each sample. But also only on the past signal, not on the signal to be encoded in the future, but on the past signal only. So this only works if the statistics does not change significantly, if the past is similar to the future. But it has the advantage that there's no site information necessary, no blocks, which means you get basically zero coding delay. Right? Because each sample is predicted immediately and can be sent immediately. So this is called adaptive differential pulse code modulation, or short ADPCM. And it's used, for instance, in the ITU standards G.726, G722, and G722.2 ITU-T speech coding standards. Right. And here I also have a Python example, which basically shows you the same thing, but now based on LMS. So let me open it. So here's now the code for the LMS. So the beginning is pretty much the same thing. I also have a prediction order of 10 as before. And I have a for loop, but now not only over the blocks, but over each sample, which you can see here. So here this n goes over the entire signal. So, and that also makes it slower, as you can see right away. If you have a for loop over many more samples, then it must become slow. And from time to time here, I'm printing the encoder coefficients. And here I'm computing the predicted value p. Right? So here I have my past reconstructed samples and multiplied with a coefficient vector h. So you can also see now I'm not doing it with the L filter. Why am I not doing it with the L filter function here? What do you think? Why am I using the dot product or the matrix product here instead of the L filter?
Because we don't need the block in the previous one.
Yeah, we don't need it if we don't have it, right?
The formula.
Yeah. So basically, when you apply L filter, that means you have the same coefficients all over the place where you apply L filter. The coefficients are fixed because they're in the argument of L filter. But here we want to update the coefficients, the filter coefficients for each sample. Right? After each sample, we update the coefficients, and that means we cannot use L filter. Right? So that makes it a little bit more complicated. We have changing coefficients. They change not just block to block, but sample by sample. So that's why I'm using this matrix product here. Basically like our formulation for Wiener Hoff, but this is done sample for sample. Yeah, and here I'm predicting the prediction error. So here I have x, the current sample, minus p, the predicted, and here I'm also including some quantization. And it turns out for LMS, quantization is crucial because everything is going into this feedback loop, and the tiniest error would lead to this feedback loop to diverge between encoder and decoder. So that's why in this case actually quantization is really important. Even if it's just a small quantization like here, 1/100th. Right? Oh yeah, we wanted to look at the prediction error so that we can compare it now. Let's see, where do I have to click? Here it is. So for LPC, you got a signal to error ratio of 61. Right? So this is your coding gain for the power. So keep this in mind, because now we will see the same for the LMS and can compare. So we have the error here, and now we need to compute the reconstructed, which is E plus P, because the error now includes quantization, and in order for the encoder and the decoder running in parallel, we need to base the predictor purely on the reconstructed samples which are also available at the decoder side. Right? So that's why we need to reconstruct here, including the quantization error that we introduced here. So that's why we need to update our coefficients using the reconstructed samples, including the prediction error, the quantization error. So here you can see our 10 past reconstructed values. So here again, this is this is the update for our coefficients. So here you can see this is the current coefficients, and they are updated using this formula that we just saw. Basically here E times the reconstructed values times the E. So this is the non-normalized, because there's no power here. It's just error times this vector of 10 past samples. And this is some update constant here. So this is actually used to play around to see which works better. Often it's 0.1, for instance. Here it turns out 1.0 is actually a good value. And this actually depends on the value range that you have for your signal. So since here I have a value range between -1 and 1, 1.0 is a good number, but if you have a value range between 2 to the 15th, -2 to the 15th to +2 to the 15th, then this should be a very small number. Otherwise, your coefficients will be too small or too large. Yeah, so here you have your constant update after each sample. And now we can compute again this ratio between the prediction error. So here's the prediction error power, the average. Here is the signal error average, and here is the signal to error ratio, which gives you the coding gain. So here you have the playback of your error sound, and then here you have the reconstruction at the decoder. So again, you start with zeros in the coefficients. Here you have the same loop over all the samples. Here you have the same reconstruction as before, and also the same update of your coefficients. So here, notice that this update is done after the reconstruction, which is important. Right. So here first you use the coefficients here for the prediction, and then you update it. So if you would switch it, it wouldn't work. And so really it depends on the right order. Okay, so let's try it out. I think 3. Oh. So, for some reason we didn't hear the original, but we already know what it is. So here you can see now the difference between the original and the prediction error. So what do you think? Do you see a difference between LPC and LMS here?
Yeah.
What's the difference?
Here we have more information.
What do you mean with more information?
But prediction error is has more bits here.
Well, it's somewhat larger, right? And you can also see here there are steps. Right? There are discrete steps here. When you look at small values, you can see discrete steps in the size of the error. Why do we have those discrete steps now? What do you think? Yeah. Here. It's jumpy, right? And it comes from the quantization, right? Here I included quantization of the prediction error. And it's important to ensure that we have exactly the same predictor and encoder and decoder. Because the slightest deviation would lead to, at some point, the decoder exploding, meaning it generates definite numbers. Right, so this actually is not working without quantization. Unlike the LPC, LPC is working with and without quantization. Here, this is only working with quantization. Yeah, so here's the reconstructed signal. It's perfect.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Could you hear the quantization noise? So this is the disadvantages of the quantization. You have quantization noise. Yeah. So, but actually you could reduce the quantization step size even smaller below listening level. So go back. So here are some references of where you use LMS. You use it, for instance, in G.726 ITU standard, then G77. Here's some links to it, and here G77.2. So here you can see Wikipedia links and also direct links to ITU. So here it takes a little time if you click through to the original standard. But this original standard is actually then used to implement the standard itself with your programmer. Yeah, here's some general references to lossless compression. There's a nice article by Matt and Schaefer in the Signal Processing magazine of 2001, which you can find in our IEEE Explorer. And there's also an article by us about perceptual coding using adaptive pre- and post-filters and lossless compression in the transactions on speech and audio processing, audio signal processing from 2002. Yeah, and then you can also use, as an alternative to prediction, you can use filter banks for lossless audio coding, which is a little bit more unusual, but has the advantage that you can combine it with lossy coding or perceptual coding like an ADC. So it's actually not so easy as this picture shows. We have some quantization, and that means we have different signal coming out of the synthesis. Right? And to choose this quantization such that we have the same integers is not trivial. Right? So this is actually not a good approach. We lose information. So instead, we use a structure like this. It's called a lifting scheme or ladder network. And instead of having a quantization, we use a rounding in the off signal paths, in the side branch. So we have some signal going through, right? And like prediction, we have some side branch which basically mix those signals, including rounding. And in this way, just like prediction, you can invert it, right? We add something on one side and we subtract something on the other side, and then we have perfect reconstruction. So here on the left-hand side, the output would be y1 would be x1 plus round of a times x0, and y1 would be x0. And the inverse step would be x1 prime is y1 minus round of a times y0 is x1, and then x0 prime is y0 is x0. So in this way we can perfectly reconstruct our system, even though we have rounding. And the interesting part is that we can decompose a so-called difference rotation, which is basically just a rotation matrix, we can rewrite this rotation matrix into a product of those three matrices. And it turns out that each of those three matrices represents a lifting step. So this is the representation of those matrices in terms of a block diagram. Right. So you can see here, this becomes identical to this without the rounding. But now you have the advantage to include rounding to make it invertible despite the rounding. Right. So you can imagine if you have integer values coming in here, then exactly the same integers, then also integer values come out here, but in an invertible way. Right. So you rotate some integer representation. It's again integer, but you are able to reconstruct the original from it using this structure here. So it's an invertible integer approximation of the rotation. So it's a little bit more tricky, but invertible. And it's interesting because the MDCT filter bank can be decomposed into such rotations, right? So we have a windowing, the time domain aliasing, which is basically a rotation matrix, and also the DCT of type 4 can also be written using those rotation matrices. Right. And yeah, fast algorithms usually provide such a decomposition. So we don't need to look far, we just look for the fast implementation. And this is how it looks like. So here we have the MDCT consisting of the DCT type 4 block, and this is the window block. So we have influences from both sides which give us this sine window shape covering neighboring blocks, and do the processing, the pre-processing and folding, and then the DCT, and this is then the subdense signals. And here we do the inverse. So the inverse is the inverse DCT4, which is identical to the DCT4, and here we do also the windowing, the overlap add of this sine window. Makes sense? So this is what we know from the MDCT lecture about the folding matrix, right? This F matrix, which is used to process our window functions. So this is basically our F matrix, the folding matrix. Yeah, so that means the MDCT can be completely decomposed into Gibbons rotations, and we can simply then replace those rotations by our lifting scheme. And the result is called IntMDCT. And then now we have MDCT that if we have as input integer values, the subband values will also be integer valued. And it also inherits the properties of the MDCT, which is perfect reconstruction, critical sampling, overlapping blocks, and also good spectral representation of audio signals. And it allows lossless coding in the frequency domain by entropy coding of integer spectral values with no quantization necessary. So here you can see the efficiency of it. So here we have a spectrum of a sine wave, as an example, at 1 kilohertz at 20 dB full scale. And you can see here, green and red is the output of the MDCT at the frequency of the sinusoid. So you can see red and green. Red is in the MDCT, green is the MDCT, and where you only see green, the red is basically just below it, which means it's identical. And then when you come to higher frequencies, basically what you have is just rounding errors. And you can see here, the MDCT goes a little bit lower because there's no rounding involved. Right? So this is basically corresponding to the computational accuracy that is used to implement it. And then here in red, you can see this is the noise coming from rounding in the IntMDCT. You can see here, we have about 10 dB more, but at a very low level. So that shows it works quite well. Basically, it has a noise Yeah, compared to the maximum is -20. Here we are at 110, so about 90 dB below the signal, and that's usually enough. To see it more closely here, the differences. So this is now a more realistic spectrum from Camino Burana music piece. And here you can see red and green again, the spectra from the two MDCT versions. And blue is the difference. And you can see here, blue is again at -110, so again about 90 dB below the peak of the signal. It's only here at the very end that you see the difference becoming as much as the signal, and that's because the signal here has nothing, because it probably was upsampled from some lower sample rate. Yeah, and then we can also improve on this for stereo signals. So when we have stereo signals, we have not just one channel, we have two channels. Right? So then we can consider those two channels together and apply the MDCT to each channel separately usually. So here we write the MDC just in terms of the DCT. So we just assume that we just have the DCT because the windowing, the F matrix basically looks very similar. So here we have the left and the right input coming from the left-hand side. And on the diagonal you can see the 1024 subband DCTs, one for each channel. Right? So that means this matrix here has a size of 2048 times 2048 here. So this is the large matrix. Each channel is individually multiplied by the DCT4. Makes sense? So we have two channels now grouped together in one large vector containing 2048 samples. The first half contains the left channel, the second half contains the right channel. So instead of processing them separately, we process them now jointly. First using this matrix, where we still keep them separate, but then we rewrite this matrix here in terms of those three modified matrices, where the DCT is now in the off diagonal. So it turns out if you multiply those two matrices, you get this original here. But now these matrices are again lifting structures. So that means you can include rounding after each DCT. And it's invertible. Right? So now we have block matrices. And that means we have fewer roundings. We only have 3 times roundings. Once from each of those large matrices. Yeah, so this is what I just said. We have now a long vector instead of 2 short ones, and we process them jointly. So this is how it looks like. So we have the left channel, the right channel. Originally they were processed separately with 2 DCTs, but now we have this structure. Left channel coming in, then we have this DCT on this off branch, and hence we can have rounding here in this off branch. Added here, then we go up, again rounding, subtracted here, and then we have another one going down with rounding and plus. So at the end of this chain, we have the left channel down and the right channel up. You can also see it by following where the left channel is going. So the left channel goes down here, DCT, and then it goes up, minus, goes down, plus, so these two cancel, and then what's left is the rounded DCT here on this side from the left channel. Same for the right. So the right goes up, and then it ends up here. So this is actually the minus right on top. Make sense? So in this way, you get joint processing of left and right channel, and you can include rounding in an invertible way. And since this way, with joint processing of stereo, you have fewer roundings, you get better compression performance. So again, the IntMDCT closely approximates the MDCT, and you can obtain a scalable combination of perceptual codec, like the AAC, with an IntMDCT. And this way we can obtain a scalable bit stream with 2 layers, which allows 2 stages of decoding. First, if perceptual coded, for instance at 128 kilobits per second, and then lossless at a much higher bit rate, and also possibly scalable. And here you can see the block diagram. Black is what you have from AAC for the encoder, and green is the lossless enhancement bit stream. So you can see here is the IntMDCT. Here we subtract what the AAC is already transmitting, so that we don't need to transmit it twice. And here is the entropy coder for the lossless enhancement part. And in the decoder we basically have the inverse, the reverse. Here black, the AAC decoded stream. And then for the lossless enhancement we have entropy decoding. Then we add it to the information that we get from AAC. And then we have the lossless audio coming out here, the bit exact reconstruction. Yeah, here's some results. Here we see the bits per sample, and we see example audio signals at 48 kilohertz sample, 98 kilohertz, 198, 192 kilohertz, and 16 bits per sample, 24 bits per sample. And this is the most common, 48 kilohertz sampling rate, 16 bits per sample. And here you can see the obtained bits. So in our case, we have AAC, it's 1.3 bits per sample, then the enhancement layer gives us 6.5 bits per sample. Together we have 7.8. If we have simulcase, if we of AAC plus some purely lossless audio coder, Monkey's Audio, then we would have AAC 1.3 plus 7.2, 8.5. So actually we get a reduction in bit rate in this way. And here you can see a purely lossless audio coder, Monkey's Audio as a reference, which has 7.2 bits per sample. So you can see that with our system we are a little bit worse than the pure lossless audio, but much better than simulcast, which means you have both complete streams. You're not using the redundancy between them. Yeah, so in conclusion, you get a lossless audio coding with filter banks. Lifting scheme or data network is an appropriate tool. And the IntMDCT allows us to efficient losslessly encode audio signals, and we have a scalable lossless enhancement of IntMDCT perceptual audio codecs like the AAC. Yeah, and here's some references for the IntMDCT. 2 of our coders, of our papers in the IEEE transactions of 2006, and here from ICAST in 2003, both available on IEEE Explore. Yeah, questions at this point? Make sense? So now you know how to do prediction, LPC and LMS, and you know how to do IntMDCT and how to do it. Okay, so
we are already past the time.
right. Thanks for your attention, and I'm open for questions.